Okay, thanks for inviting me to give this talk here today. In my talk, we talk about secure smart contracts with Isabelle Solidity. As mentioned already, my name is Diego Marmsoler from University of Exeter, and this is joint work with a couple of other people, in particular Achim Brucker, which is also part of the audience here today. Now, before we start, a quick poll. So who here is familiar with blockchain? Okay, quite. Who is familiar with smart contracts? Okay, good. Okay, more than expected. So probably you all know smart blockchain from the in the context of the FTX collapse. But in general, blockchain is a novel technology to store data in a decentralized way. And indeed, it was invented for the purpose to enable cryptocurrencies, but it also found applications in several other domains, such as healthcare, identity management, and others. And conceptually, this is how we can depict a blockchain. It's basically just a sequence of blocks where each block contains a list of records or entries which record transactions of funds from a source address to a target address. Now, one key innovation which comes with blockchain are so-called smart contracts, which are basically digital contracts which are deployed to the blockchain and executed once certain conditions are satisfied. For example, we can have a buyer. We can have a buyer and a seller here, which agree on some predetermined conditions for a sale. They would formalize it in the form of a smart contract, push it or deploy it to the blockchain, and at a later stage, when the conditions are satisfied, for example, when the buyer gets the goods, the smart contract would execute and modify the state of the blockchain. For example, release the payment to the seller. And every day, hundreds of thousands of new contracts or smart contracts are deployed to various blockchains, managing millions of dollars worth of transactions. And smart contracts are usually developed in a high-level programming language, and the most popular of which is Solidity. And indeed, Solidity is the Java of blockchain, I would say, or nowadays maybe more the Python of blockchain. But indeed, 85% of all smart contracts nowadays are developed in Solidity. So it's the gold standard of smart contract development. And this is a simple Solidity contract which implements a banking application. And the idea is that a client can basically deposit some funds and later on withdraw them from the contract. And indeed, it's quite a simple contract, but it showcases many of the characteristic features of a smart contract, and therefore it's worth having a closer look. And the first thing you need to know about smart contracts is that once they are deployed to the blockchain, they basically have an associated account on this blockchain where they basically keep track of the funds which they own. Now, the idea here with this simple contract is that the contract keeps an internal record of the contributions of each of its customers to the balance of the bank. And now, if you look at the implementation of the deposit function, we can see one characteristic function or feature of Solidity in particular, but smart contracts in general. It's this payable keyword here, which basically says that this deposit function is a payable function, which means when we invoke it, we can transfer funds with it. So when a client now calls the deposit method, they can basically send some funds with it, which are then transferred from the client's account to the contracts account, and then we execute the body of the deposit function. And in the body, we can then, when programming the contract, we can then access the address of the caller of the function, which is in Solidity, it's denoted with message sender, and we can also access the amount of funds which were transferred by calling the function, which is message value in Solidity. And so what we do here, whenever someone deposits some money, we just add it to the internal balance of this customer. Quite simple. Now, the implementation of withdraw is straightforward and almost self-explanatory. So we first look up the funds which were contributed by this particular client, by the sender. Then we reset their balance to 0, and then we use a built-in function, transfer here, to transfer funds from the account of the contract to the account of the customer of the sender. Okay, so the customer can withdraw everything at once. Now it's also worth to look at how we can use this contract, which showcases some additional characteristic features of smart contracts. This is an example customer contract which basically uses our banking contract. And it contains a reference to its bank, which is given to the customer when it is deployed to the blockchain. And then it just implements two methods, deposit and withdraw, which delegate the call to the corresponding deposit and withdraw function of the bank. And the only really interesting thing here is the value keyword, which is again a built-in keyword in Solidity, which allows us to set the amount of value of funds which we would like to transfer with this method call. So here we transfer V amount of currency from the customer to the bank, and then we execute the deposit function. The withdraw just delegates the call to withdraw. And then we see another function here, which is a source of a lot of problems in the context of smart contracts, which is a so-called fallback function. And this function is executed every time when the customer receives some funds from someone. In this case, if we call bank.withdraw, then eventually withdraw will transfer some money to the customer, which means the funds are transferred from the customer, from the bank to the customer, and then an implicit or an execution of the withdraw of the fallback function is triggered implicitly. And this is a source of many bugs in the smart contract world where this function was exploited. Well, now what is the problem with smart contracts? As I've told you, so smart contracts are basically just a particular type of program code which is deployed to the blockchain and executed by sending special transactions to it. And therefore, as you all know, since it's program code, it not only can contain bugs, but it usually does contain bugs. Now, what makes this bad, particularly bad in the context of smart contracts, is that, as I told you at the beginning, smart contracts are often used to automate financial transactions, and therefore exploiting these bugs usually results in very high economic losses. And there's many examples from the past where this happened. So a very famous example is the DAO attack from 2016, where a vulnerability in a Ethereum smart contract was exploited in the fallback function. It was a problem with the fallback function. And this resulted in a loss of approximately $60 million and a subsequent fork of the blockchain. Now, in general, it is estimated that since 2019, more than $5 billion were stolen due to vulnerabilities in smart contracts. So this is a lot, and therefore we would like to verify our contracts before we deploy them to the blockchain. Because once they are deployed, it's only difficult to remove or to update them anymore. And this is where our research, or what our research is about. We try to build tools for the verification of smart contracts. Now, to this end, we developed Isabelle Solidity, which is a deep embedding of a subset of Solidity, O516, in Isabelle Hall. And we support many of the features which are characteristic for Solidity. For example, fixed-size integer types with and without overflow, or domain-specific primitives such as transfer or balance queries, or also fallback methods which are automatically executed once we receive funds. And also a characteristic function, feature of Solidity is that a Solidity program has access to 4 different types of stores. And to make it worse, the semantics of certain statements depends on the store in which the data is located, which makes it quite a challenge from the viewpoint of verification. And finally, we also have an extendable GAS model to model computational costs. So GAS is Solidity's way to model computation explicitly, and in our formalization, we allow the user to provide a custom GAS model for their particular context. Now, one of the design goals of Isabelle Solidity was to try to be faithful to the original specification of the language, which is a challenge when we build models. And to this end, so the first thing, what we did is we made sure that Isabelle Solidity, our semantics, is executable. So we can execute programs with our semantics and compare them or test them against a reference implementation. And to even more, we basically implemented a custom fuzzy testing framework which would randomly or automatically generate random Solidity programs, deploy them to a blockchain, execute them on our semantics, and compare the outcomes, which allows us to run a lot of tests automatically to basically gain confidence that our semantics conforms to the original specification. Now, we successfully used Isabelle Solidity so far in various case studies. The first one is a verified constant solving use case in which we basically implemented a tool which optimizes given Solidity programs with respect to gas costs. So the tool would take a Solidity program and try to optimize it to reduce the gas costs. And then we used Isabelle Solidity to verify that the tool does not modify the semantics of the original program. Now, in the second case study, we used Isabelle Solidity to verify soundness of a calculus, SS-calc, which can be used to verify invariance for Solidity contracts. So we proved that if the calculus tells us that an invariant holds, then it indeed does. And finally, we used Isabelle Solidity to verify a concrete contract, in this case, the banking contract I've shown you before. We used it to verify an invariant for this contract to demonstrate that it can also be used to verify individual contracts. Okay, to conclude this talk, let me briefly summarize what we have achieved so far. So we formalized a subset of Solidity in Isabelle Hall, and there's 2 important aspects to this formalization. So first, it's a conservative extension which guarantees semantic consistency of our model. And second, it's a deep embedding which allows us not only to reason about specific contracts, but also about the Solidity language itself, and as a consequence, about the soundness of tools and methodologies which work with Solidity. However, the case studies also revealed some limitations with our approach. Oh, yeah. We also used it in 3 case studies, as I mentioned, which indeed show that we can use it for not only verifying concrete contracts, but also tools and methodologies for Solidity. But they, as I said, they revealed also some limitations of Isabelle's Solidity. In particular, the verification of individual contracts turns out to be quite a lot of work, a lot of repeating work, and therefore we are currently working on a more shallow embedding of Solidity in Isabelle, which is optimized for the verification of individual contracts. So basically what we give up is the flexibility to reason about the language itself, but what we gain is a higher degree of automation when we verify individual contracts. And we already have some first results in this area, which should hopefully be published soon, which are very promising from the automation point of view, because it shows, or we were able to decrease the effort to verify contracts a lot by this new embedding of Solidity. I think I should have some time for questions. So if there are any questions, I will hope I can answer them.
Indeed, as Diego said, there is time for questions. So if anyone has any.
I have a few questions, but I've been asking too many questions. Thank you. So transfer, strictly speaking, in the world of EVM, is not a contract call. One question I have is, how about formalization of contract calls? And one thing I have seen with theorem provers of 2 or 3 work that I've attempted, there is 1,024 deep depth to the calls that they can make, or you can make. Most of them fall on their faces a few depths, and then they do continuation, handing it off to Java or somebody else to do the rest of the work and get the computation back from them. What have you hit this problem still? That's one thing. The other thing is, I have not yet seen semantic characterization of security attacks in the world of smart contracts. What have you done in that area as well? Thank you.
Okay, a lot of questions. I will start with answering the one I think I understood the best, which is the how do we define, or what do we actually verify when it comes to smart contracts? And what I can show, I have here an example. I didn't have time to talk about it. It's this simple contract here. And I can basically talk a bit about what we verified here. So we are mostly, when we verify smart contracts, we are mostly interested in invariants, which basically describe the relationship of member variables and the balance of the contract. And we then try to verify that they hold during the whole lifetime of a contract. And for example, in the context of this banking contract, and so you remember that's the contract I explained before, what we verified is basically that the balance of the contract, which is denoted with this blue balance here, which is the balance associated with the contract's account, is greater or equal to the sum of the internal balances. And this is an example of what we verified, and what we would not have been able to verify this on contracts which led to reentrancy bugs. But the problematic thing is that in some modern, or in some implementations which implemented some similar contracts, what they did is they first transferred the money, and then they reset the balance. And if we would have tried to verify such a contract, we would not be able to verify this invariance, so we would have spotted the problem. I mean, now we know about reentrancy bugs already, so it's easy to say, but reentrancy bugs would basically violate this property here. Yeah, is it clear why we have a less equal sign here and not an equal sign? Any ideas? Sorry?
I suppose that when you create the bank contract, you send the bank some money.
Yeah. Not just the creation, but you can just gift the contract money if you want. So we basically, I mean, it wouldn't make sense, but you can just gift it. Indeed, when I tried to verify this property, I first had equality, and I saw some papers published where they indeed proved equality. So I tried to prove it as well. I failed because it turns out it is possible to gift money to the contract without being recorded, so without going through the deposit contract method, and so the invariant is less or equal, but that's fine from the contract point of view. Yes?
So one more question, Sophie, I'll just have it.
I saw that you mentioned some of the earlier works on contract verification in your slides. You didn't mention it in your talk, and in particular Laura Kovac's work, but I know that there have been some other guys who have been verifying contracts. So I suppose you have the answer to how does your work compare to theirs. And related question, there are lots of attacks where you kill the owner of a contract and then, so they are liveness attacks. And can you deal with those?
Okay, wait. The first question is how does our work relate to existing work? And there is indeed a lot of work going on in the, well, now after FTX there is less funding available. Previously there was more funding available to investigate smart contracts, but still there is a lot of work going on. And now there is most of the work which I know about, they focus on the they try to analyze smart contracts for some existing for some known vulnerabilities such as reentrancy attacks. So they do static analysis to detect if this contract is vulnerable to reentrancy or other things, and less on they focus less on the verification of invariance or functional correctness of contracts. So that's one difference. Then there exists some approaches which basically try to use model checking to verify invariance. So basically, there's two things which are different here. So one is what I mentioned here is that many of the approaches which we have seen, they basically rely on several axioms in the formalization of their approach, and therefore, so we try to avoid axioms and basically focus on a definitional extension of Isabelle to have a higher guarantee of semantic consistency. And indeed, as I said, I found papers where they proved the equality of the balance, which basically there's a high chance that just one assumption, that they had one assumption in their formalization, one axiom, which allowed them to verify this property, which was not true. And I think that's one of the differences. And the other is that by using a theory improver, we can verify properties which are out of reach for model checkers. And what was, there was a second question?
The second question on liveness, but would you be able to make it
I make it very short. Yeah. We didn't try it yet, so I don't know if it works, but we are working on a benchmark for verification of solidity programs, and it's probably a good idea to, or a good hint to put in some examples also regarding liveness properties. Yeah.
Thank you very much.